We're going to be doing a lab on calorimetry, and this is a great extension for the specific heat problems that we've been working with. So we have a lab technique that involves one material losing heat energy and another material gaining heat energy. The material that loses heat energy is going to be a piece of metal that's heated up in a beaker on a hot plate. And the material that gains energy is going to be the water that's inside of our calorimeter. So if you look at this diagram, this is our coffee cup calorimeter. This is what we use. It's not perfect, but it works pretty well. This calorimeter is two cups, one nestled inside of another. You can see there's a thermometer, a stirrer, there's a lid that fits very, very well, and there's some water inside the calorimeter. After we take that piece of metal called an ingot out of the beaker that it's been heating in, we're going to add it to this calorimeter very, very carefully, and we're going to measure the temperature change. When we have a temperature that appears to be at equilibrium, we're going to record that data, and we have to watch very carefully because we don't want to wait too long to measure the temperature, because if the temperature of the system starts dropping after it's gained, then our data will not be accurate. So if you think about it, the heat energy from the ingot, the piece of metal, very, very hot metal, is going to be transferring to the water. So the water is absorbing the heat energy and the ingot is losing the heat energy. That amount of heat energy is equal. So if you look at this picture here, we have some ingots in the diagram up at the top. This is what we're talking about. These are a little bit nicer than ours, but this is something like what we'll be using. So these pieces of metal have a string on them. This is kind of a nice cup. We don't have those. We have cheapo coffee cups. So this is kind of like our setup once we put the ingot into the coffee cup. If you look at this equation right here, it says that the negative heat energy of the warm substance is equal to the heat energy of the cool substance. So what that means is the energy lost by one material is the energy gained by the other. The minus sign here is heat energy that is lost. So remember, warm objects transfer their heat to cooler objects. So in our class, the warmer object is going to be a metal and the cooler object is going to be water. So if it's true that negative Q of the warm substance equals Q of the cool substance, then it would also be true that negative MC delta T of the metal is going to equal MC delta T of the water. And C and SH are the same thing. They're specific heat. Now, whatever you have to be solving for, of course, has to be in a rearranged equation. So you will always have to rearrange this equation. You'll never just try to solve for one thing using this basic equation here. So make sure you have a basic equation and a rearranged equation. There's no need to write anything down here. I just want you to follow with me. I'm going to go through the next couple of slides, and if you just pay attention, you're in a good place. Focus. You can go back and take notes on this and look at it more closely. At home, it's on the wiki page. So in this particular calorimetry experiment, we have a 40-gram piece of pure iron, and the temperature of that iron after it's heated up is 78.0 degrees Celsius. This is dropped into a calorimeter containing water that's initially at 22.0 degrees Celsius. After a few minutes, the temperature inside the calorimeter, it raises to 25.6 degrees Celsius. And there's some stirring going on there, and you want to be very careful that you catch the temperature at the highest point before it drops off. This temperature here is going to be the final temperature of your ingot, the metal, and it's going to be the final temperature of the water for both of those things. So you see 3 temperatures up here. That's all you need. There's not a fourth. So the basic equation is stated. We need to have 2 specific heats, one for iron and one for water. You should know the one for water. The one for water is going to always be, for our purposes, 4.184 joules per gram times degrees Celsius. In terms of the other specific heat, you're going to have to look it up in a table, but here it is. You can see both of the delta T problems right here. This is the final temperature of the system, and it's also the same over here. And then you're subtracting the initial temperature of the metal off, and you're getting a negative temperature right here, which again just reinforces that heat energy is lost. Over here, your initial temperature is 22.0 degrees Celsius, so your delta T is going to be 3.6 degrees Celsius. It's only 2 sig figs now, which is kind of odd, but we have a tenths place here and we also have a tenths place here. Over here we end up with 3. So just keep in mind you have to handle your significant figures properly. So at this point, what we have to do is think about this. If we're solving for the mass of the water, how are we going to rearrange that equation so that we can have MW on the left and everything else on the right? Well, what we would have to do is, if you look carefully at the equation, is we simply divide both sides by the specific heat of the water and the delta T of the water. So basic equation, and you can see the rearranged equation about halfway down the page here. So this rearranged equation must have the unknown that you're trying to find on the left side. Everything else is going to be on the right. Now, this negative sign has to stay right in front of all of the measurements for the metal. On the bottom, this is the water, and on the top, this is the metal. So you can go ahead and plug everything in. Here is the mass of the metal. Here's the specific heat of the metal. And here is the delta T of the metal. Here is the specific heat of water, which you do have to know. And here's the delta T of the water. Now, do not forget, you have a negative sign right here. Okay. You have a negative sign right here as well. So what's going to happen here is if you multiply a negative by a negative, this is going to become positive. So keep your eye on that. So unit cancellation before we go anywhere else. The specific heat units cancel and the temperature units cancel. Our final unit is going to be grams, which is perfect because we are talking about water here. We need to know the mass of it. This is what we are solving for. So once you multiply the mass times the specific heat times the delta T of the metal, and you divide by both the specific heat of the water and divide by the delta T of the water, you should get somewhere around 62.4 grams. If you look back up at your significant figures, you have 4, 3, 3, 4, and 2. And so we'll just simply round it to 62 grams of water. You have to keep in mind what you're solving for because we want it labeled. M subscript W is fine, but if you put it out to the right, that's much better. So this is your first example for calorimetry. Hopefully you did not write anything down here. I'm going to end this section of the podcast right now because I know I can't get through everything in 15 minutes. So I'm going to pick up on this slide when I get back to you.